So what we are going to study today is we are going to have a continuous sorry. What we are going to see is we are going to study. We yesterday studied the differential form of the Gauss's law. Now continuing with that discussion, we can have some detour into अगर आपको याद है scalar potential and vector potential. So how we can redefine potentials, the traditional definition of potentials appropriately, or readjust our definition of potentials appropriately, not by these general definitions. How we define a scalar potential, B is equal to, and vector potential, B is equal to del cross A, है ना. एक नॉर्मली हम कैसे करते हैं ना, we define E is equal to minus del A. We also write it then like this, del A plus, we write it as del V. Under the definition of V in terms of A, we also write it as like this. And B को हम ऐसे भी define करते हैं, है ना. So why we did it? हमने, if you remember, in your exercise in the exercise which you have done in, so it will leave things intact. It will leave things unchanged when you have these sort of substitutions in the Maxwell's equations. So there is a particular analogous. The way we have a definition, analogous of potential in electric field. Similarly, we should have an analog of potential in the magnetic field. So that's why we took a recourse to this very way of defining B in terms of del cross A. So curlless field, so anything जिसका divergence of curl will come out to be 0. So if you just go to that very discussion, अब उसी को if we have another equation of equation of electrostatics and static potential. So how we define it? For example, so divergence of curl, del cross E, है ना. ऐसे भी आ सकता है कि E का अगर del cross minus del of E is equal to, है ना, you can see it. And so from Coulomb's law, we can also write Coulomb's law in terms of electric field. We can also write it like this. This is the charge density है कि नहीं, d3x. Can you write it like this? है ना, ये क्यूब है, ये 1 तो यहाँ स्क्वायर आएगा. That's basically electric field is inversely proportional to. So this is another way of writing it in the integral form. So if you write it in the integral form, so we can also write x minus x prime. को हम ऐसे भी लिख सकते हैं. लिख सकते हैं कि नहीं? Because once cancels, है ना, यहाँ स्क्वायर आएगा डिनोमिनेटर में, तो डाइवर्जेंस ऑफ इसका ये d by dx 1 by x square आएगा. You can write it like this. This is a gradient of a scalar function is like this. So gradient of function, some function which is defined like this. So अगर हम gradient operator involves x, in gradient operator involves x, operation involving x, then integration variable अगर हमारे पास x prime है, then and if we keep it outside the sign, integral sign, electric field can also be written as 1 by 4 pi epsilon naught delta integral of you can write it like this. 1 by 4 pi epsilon naught del like this है ना, del हमने इंटीग्रेट किया आउटसाइड, so if you multiply it by inside it will again it will do this thing, ये x square आएगा, but here it's x cube, since we have put एक इसमें numerator में, we can also write it like this. And if you write it like this, so further we can say that curl or gradient of any well-behaved scalar function of Poisson equation vanishes. अब ये है ना कि del cross gradient of a scalar, any scalar function vanishes. Del cross of del of psi will come out to be 0. So that's it. So अब इसी चीज को if you want to write it further, we can write it further here. We can write it further. We can write it. We can write it further. E will write it as minus del of phi. Huh? Phi we can write it as x minus x prime d3x. लिख सकते हैं? Phi is the potential. It is the gradient of this potential. So phi we have written in terms of this is rho. Rho is the charge density, है ना? So you can see charge per unit volume. Since volume is here also, yes, we can see it, right? So you can write it like this. This is another way of writing the same thing. और अगर आप scalar potential की in terms of we want to have a physical interpretation of scalar potential. We want to have physical interpretation of scalar potential. So what we are going to do? We are taking recourse for our previous definition of force in terms of charge. ऐसे है. We can define force in terms of this thing, and we have to see what is the way we do work done in taking, just like we do work in classically. Work done is taking a point particle from position A to position B. So work done F dot ds is equivalent to difference of the two. So in the same way we are here not taking point mass, we are not taking point mass in a gravitational field, we are taking a charged particle in an electric field, and the charged particle is moving from position A to, so it has some displacement f dx from dx1 to dx2. The same thing can be written if we want to write work done, we can write it as A to B. So if it's B to A, you can have minus also, you can have plus also, you can flip the sign. So f dot dl. So f is QE minus QE dot dl from point A to point B. Okay, so this much you know. So now what we are going to do is from this we are going to do so work done of a charged particle in the case of electromagnetic field is Q times A to B. So E के बदले क्या है? E is equal to it's del of V. It's del of V. So we can write it as del of V. Del of V, yeah, we can also write it in terms of phi as a scalar potential. That would be better way of writing it. Phi. Dot of this line element dl. This line element is from point A to point B. So you are doing it. What's the work done of a charge particle moving from point A to point B in a given electric field? with given this under potential, having potential phi under this redefinition of electric field. So it will come out to be this. So if it is this way, so work done can further be Q times अब देखो यहाँ पर it's del, you know, d by dx of I, d by dy of j, d by dz of this line element is what? You can also further say this line element is dxi, dyj, and so we have a dot product of this vis-a-vis d by dx of I, d by dy of j, is d by dz of, है ना? So if it operates on this thing, so d by dx it will be I plus j plus k. So it will be there, it will be sort of one आएगा ये, आएगा कि नहीं? ये d by dx of I plus j plus k आएगा, I plus j plus k. So you can write it like this. So phi, it's 2. So this phi और d phi अपना हमारे पास आएगा d phi by dxi, d phi by dyj, d phi by dzk. Dot product of dxi, di. So it's basically d phi. इसका multiplication है इसके साथ. So you will get, when you have dot product of this thing, it will get d phi. You will get d phi. So the d phi is from point phi b minus phi. ठीक है? So this is how. So if you want to geometrically try to understand it in terms of geometrically, कोई भी, this is an electric field. So these are electric lines of force flux, lines of force. So we are trying to move a particle from point A to B. So this is the line element. आप लिखिए यहाँ से यहाँ तक. It's the line element di or dl. This line element. And this is force. This is charge. This is electric field. This is B. This is A. Got the point? So this is clear. So work done will be equivalent to this. So you can write it like this, or work done means work done is equivalent to E dot dl. है ना? You can also you can have this W by Q is equivalent to Q times phi b minus phi A. है ना? Now what we are going to do, this work done per unit charge, this if you write it here, this is Q. So we can write W by charge, more than per unit charge, इसके बदले we will write it this line integral. So we have got a particular definition of line integral from point A to point E dot dl किसके बराबर है? Phi b minus so this is what we have got. So E dot dl, the electric field का dot product with the line element. It's as if line element is this moving from point A to point B. It is as if you have the difference of potentials, उसी को हम gradient कहते हैं. So potential difference between 2 points is given by dot product of electric field between 2 points in a finite country. ठीक है. अब उसके बाद later you will have these conditions whether the field is conservative or not. So if you start from the given point and you come back to the same point, net work done is zero. So that comes up our definition. So from that you can extract that definition from this understanding that if you started from the same point and you went from A के बाद में you again reached A, है ना? This is also known as closed integral, है ना? So you can write this thing as this is known as conservative field. अब ये आप you have been reading that magnetic field is not, वहाँ B dot dl is equal to mu naught I. So more than in a magnetic field, in a closed loop, it will not cancel. So you can have this understanding. So that's not. So that's what I'm trying to say. Work done in an electric field is this. It's basically difference of potential. Is basically where this E dot dl between points A and B. And in case of a closed loop or closed path, it's like this. And you can have, if you want to just like yesterday, we tried to reimagine the Gauss's law की definition को हमने कैसे imagine किया? We tried to imagine it in terms of हमने Gauss divergence theory use की थी, है ना? Trying to write the same thing here. हाँ, Gauss's law का differential form of the Gauss's law. हाँ, so in the same way you can use here Stokes theorem. Stokes theorem में है ना, how you can Gauss's theorem में how you can convert a surface integral into volume integral, है ना? Left hand side में you have surface and right hand side में. In Stokes theorem, left hand side में you have a closed loop line integral and right hand side में है surface integral. So closed loops में जो होगा surface integral, you can have this thing. So you can A dot dl is also written as curl of that quantity. So this is closed line integral. This is ds surface integral. So you can use the same definition here also. A के बदले आप replace कर सकते हो E. The same way, just like we have Gauss's differential law, Gauss law in the differential form, we can use the Stokes theorem here also. ठीक है? This is my origin. Stokes theorem में क्या ऐसे total bounded ऐसे हम we define it in terms of curl of all surfaces निकालते हैं inside a given loop. That could be as if you are calculating the boundary along that thing. Got my point? So this is the understanding. जिस तरह हमने कल Gauss's law in differential form use किया था. The total charge divergence of that quantity in a given is equivalent to the surface total flux outside the surface. You can have the same thing here also. So this much is clear. So now what we are going to do is we are going to have surface distribution of charge and dipoles, and I'll not write it. So how charge and dipoles are on the surfaces, and what are the discontinuities? What are the discontinuities of E and B fields? So on a given surface there are, जिस तरह हम यहाँ करते हैं ना, so E dot dl जो A to B है, it's like closely when you calculate work done, ये होगी ना क्लोजली रिलेटेड रीजन्स इन स्पेस या क्लोजली नेबरिंग लाइंस, नेबरिंग रीजन्स, एफ डॉट डी एस, सो डी एस टू माइनस डी एस वन है ना, क्लोज पॉइंट्स, नेबरिंग पॉइंट्स. सो इन द सेम वे surface distribution of charge are distributed and they are distributed on a given surface. Now what are discontinuities and ये B fields. Discontinuities किसको आप कहेंगे? उसकी वजह से चार्ज सरफेस पे हैं एंड क्लोजली जो क्लोजली रिलेटेड चार्जेस, एक चार्ज यहाँ पे एक थोड़ी सी उससे जो discontinuities आएंगी in the medium surfaces, we have to study those things. What my point? Discontinuities आएंगी in terms of E and B fields की measurement. For example, electric field आप normal surface charge की वजह से आप simply करते हैं ना, ऐसे is equal to sigma by epsilon. तो एक sheet of charge है ना, मगर अगर उसी sheet पे दूसरा sheet of neighboring closed sheet of charge, can you get the same contribution or not? ठीक है, this is the point we are going to study. Besides that, so E2 minus E1 dot of n is sigma by epsilon. तो अगर हमारे पास फॉर एग्जांपल गॉसेस लॉ, ये जो इलेक्ट्रोस्टैटिक्स में प्रॉब्लम है ना, पोटेंशियल फॉर्मिंग ड्यू टू पोटेंशियल फॉर द गिवन डिस्ट्रीब्यूशन ऑफ चार्ज हमारे पास होती है ये. बट अब हमारे पास इफ यू हैव टू सी, इफ यू हैव a unit normal for two what is the electric field due to this charge due to on closely related surfaces, on closely which might have consecutive or subsequent electric field का value क्या होगा at surface E1 and at surface E2 due to this charge distribution sigma. तो अगर हम इसको ज्योमेट्रिकली डायग्रामेटिकली देखेंगे, for example, this is sigma charge distribution, this is unit vector n, this is field due to it E2 और यहां से जो फील्ड है ये E1 है, ये साइड 1 है एंड दिस इज साइड 2, दिस इज साइड 2, दिस इज साइड 1. ठीक है, तो इस साइड में एक होगा, इस साइड में दूसरा होगा. ये इलेक्ट्रिक फील्ड इसका इस डायरेक्शन में होगा, इलेक्ट्रिक फील्ड इसका इस डायरेक्शन में. दैट्स व्हाई वी आर टेकिंग इट माइनस. सो दे विल बी फील्ड्स विल बी opposite direction में होगा. So that's why we are taking as it will be equivalent to a net charge on that surface, that's given by sigma. Okay, so this is the discontinuity in the normal component of electric field on surface of charge, on surface layer of charge. Now what we can do is we can use the same thing here. We can use rather than trying to write it in terms of sigma, so we'll write it in terms of we will try to write it in terms of phi. The way we have tried to define, redefined phi, the definition of phi, electric field in terms of phi, as a gradient of potential. E को हमने define किया as a gradient of phi 2 minus phi 1. And what is the sort of work which is required to move a charged particle from point A to point B? With that understanding, we are going to redefine our definition of potentials in terms of surface charge distribution. In terms of phi को हम in terms of sigma लिखेंगे. हमने वहां सिर्फ स्ट्रेट अवे किया था कि phi 2 minus phi 1 is equal to E dot dl, है ना, लिखा था in terms of work done. So what we are going to say, we are going to redefine phi in terms of some definition of potential, which is 1 by 4 pi epsilon naught, and that we have to define. We have not to define charge, we have to define surface charge on a given surface. ठीक है? Normally phi को in terms of q by 4 pi epsilon naught r1 minus in terms of r1 and r2 लिखते हैं. तो we'll write it in terms of q नहीं होगा, यहाँ surface charge distribution होगा sigma x prime. So if it's surface तो यहाँ आएगा area element. We'll have an area element here. So now if you want to diagrammatically further see it, if you want to diagrammatically further see it in terms of two closely neighboring surfaces, तो हमारे पास अगर surface A है, this is surface so these are two surface layers, closely related surface layers having charge sigma and sigma minus. I can see it, or you can write it as limiting processes involved creating a dipole layer. Dipole layer कैसे बनती है? Dipole, how we define normal dipole? Dipole is the charge into 2D. अब यहाँ जो चार्ज है ना, इट्स द सरफेस पे क्या चार्ज, ठीक है, तो उनके दरमियान क्या डिस्टेंस होगी, तो क्लोजली रिलेटेड टू सरफेसेस क्या है, ठीक है, एंड उनकी वजह से क्या डिस्टेंस है जिसकी वजह से डायपोल प्रोड्यूस हो रहा है. सो यू गॉट द पॉइंट व्हाट आई एम ट्राइंग टू से. सो इफ यू वांट टू राइट इट इन टर्म्स ऑफ, फॉर एग्जांपल द सेम फिगर को अगर हम वेक्टोरियली रिप्रेजेंट करेंगे एक लेयर का, फॉर एग्जांपल दिस इज वन लेयर. So we are taking analogy of just like हमने potential you can bit late, जिस तरह हम potential difference define करते हैं ना between two closely neighboring point का gradient, that way we define electric field, है ना, E is equal to delta phi. Phi goes from phi A minus phi B. So in the same way we are here constructing two closely neighboring charge की layers, दो layers, उनके दरमियान जो distance है उसकी वजह से dipole create होता है. This is our point, and that for that first we define phi in terms of charge. I see. This is what we are doing. So now if we define closely near charges का in terms of area element A है, dA prime ये dA double prime है. So we want to write it vectorially. ऐसे हम vectorially लिखेंगे. Point O x prime minus n dx. ये है ना, ये है, ये देखो, दिस इज x डिस्टेंस, दिस इज a डिस्टेंस यहां से यहां तक. सो ये n डॉट dx है, बेसिकली n डॉट dx है. ये है ना, अगर ये एन डॉट कॉस जीरो आएगा तो ये पूरा पर्पल, ये दिस एंड दिस लाइन विल बी सेम। ये लाइन जैसे ट्रायंगल ऑफ वेक्टर्स है ना, ये यहां से यहां तक। तो बट इट कैन बी, क्योंकि हम दो लेयर्स ले रहे हैं ना, सो यहां से यहां तक जो ये डिस्टेंस है ना, ये डिपेंड करेगा यहां से एंगल कितना है। सो इफ एंगल इज जीरो तो दिस लाइन विल कोइंसाइड विद दिस लाइन। इफ इट विल नॉट कोइंसाइड, ये इसमें कुछ होगा अपना ये, ठीक है। So for closely two neighboring layers of charges, जिसकी वजह से डायपोल प्रोड्यूस हो रहा है at some given point O, we are going to do our this just like we try to find work done for a given charge from point A to point B in terms of difference of potentials. We are doing the same exercise here for surface layers of charge. It's a sort of physical realization, क्योंकि नेचर में पॉइंट चार्ज नहीं होता है, डिस्ट्रीब्यूशन ऑफ चार्ज होता है या सरफेस चार्ज डिस्ट्रीब्यूशन होता है। जैसे करंट आप देते हैं, ठीक है, वो स्लाइटली पोलराइज होता है कोई भी मटीरियल। तो अगर हम दोनों के लिए लिखेंगे 1/5x 1/4πε0 सिग्मा x प्राइम, तो ये ए के लिए दिस इज फॉर, चलो यहां से यहां तक इसका सरफेस चार्ज क्या है, दिस टर्म। फॉर दिस इट विल बी दिस, इट विल बी सिग्मा एक्स प्राइम बी ए डबल प्राइम, ये है ना बी ए डबल प्राइम, इट विल बी एक्स माइनस एक्स प्राइम प्लस एन बी, है ना। यहाँ खाली x माइनस एक्स प्राइम है एक में, दूसरे में है x माइनस एक्स प्राइम प्लस एन डी, दिस प्लस दिस, ये आ गई x माइनस एक्स प्राइम प्लस एन डी, ये एन डी ये वाला है। अब देखो ये यहां से यहां तक x प्राइम, यहां से यहां तक x हो गई ना x माइनस एक्स प्राइम एक, दूसरा होगा x प्राइम माइनस दिस, सिंस इसका स्लांट एंगल है, दैट्स व्हाई दिस एंड डॉट डी इज सब, ये माइनस है यहां पर, माइनस माइनस प्लस हो जाएगा, ये माइनस आएगा। नाउ ये अप्लाई टेलर्स सीरीज है। टेलर सीरीज में अगर आप करेंगे काम, ये डिनोमिनेटर में है ना x माइनस एक्स प्राइम प्लस एन डी माइनस 1, सो वी आर गोइंग टू यूज टेलर सीरीज। टेलर सीरीज आपने दिया है ना, f of x plus h is equal to a f of x plus a factorial। what does it mean? it means कि कोई भी फंक्शन कोई भी है, उसका जो क्लोजली जो उसका नेबरिंग पॉइंट है ना, उसका आप डेरिवेटिव लेते हैं एंड फिर वो कोई भी एक्सपेंशन करते हैं along that point in the closely neighboring points के हिसाब से, उस हिसाब से लिखते हैं फर्स्ट, वो रोक्स फॉर्म ऑफ रिमाइंडर लेते हैं, फर्स्ट डेरिवेटिव सेकंड डेरिवेटिव। इन द सेम वे दिस इज अ क्लोजली फर्स्ट टू टर्म्स लेंगे इसके, ठीक है, एंड अप्लाइंग द टेलर्स थ्योरम, टेकिंग a is very very less than x and 1 by x plus a, 1 by x plus a को हम करेंगे दिखाने के लिए, ये 1 by x plus a टाइम्स डेल्टा, ये फर्स्ट टर्म है हमारी, a इंटू डेल्टा 1 by x, सेकेंड टर्म आएगी डेल्टा a इंटू डेल्टा 1 by x स्क्वायर, ऐसे आएगा 1 by x क्यूब, वो हायर डेरिवेटिव्स ऑफ द टेलर्स थ्योरम आएगी। सो इफ यू अप्लाई टेलर्स थ्योरम, जो phi x है, सो फर्स्ट टर्म जो हमारे पास आएगी phi x पोटेंशियल ऑफ ड्यू टू दिस सरफेस चार्ज, ड्यू टू दिस सरफेस चार्ज। अब यहां हम सिर्फ काम करेंगे, एक काम करेंगे यहां पर, सो द बुक हैज यूज्ड सिग्मा को फर्दर ही इसने इन टर्म्स ऑफ डायपोलर डी की, इन टर्म्स ऑफ डी डिफाइन किया है, सरफेस चार्ज को इन टर्म्स ऑफ D डिफाइन किया है. So we can write here D, and using our definition of Taylor's expansion in different orders of expansion, इसको हम इसी में लगाएंगे. ठीक है, तो या तो यहां पर तो सिग्मा, चलो ये आप अपना रखो सिग्मा, यहां पर सिग्मा के बदले सिग्मा इंटू एरिया इंटू डिस्टेंस, इसके बदले आप ये रखो. चलो यहाँ ये जो डॉट लिखी है ना यहाँ पर, इट्स एज इफ यू आर एक्सपेंडिंग डिफरेंट टर्म्स इन द टेलर एक्सपेंशन, डिफरेंट टर्म्स इन द डिपेंडिंग अपॉन x माइनस एक्स प्राइम, डिपेंडिंग अपॉन x माइनस एक्स प्राइम. जैसे यहां से यहां तक कितना डिस्टेंस है x, मगर यहां से ये डिस्टेंस ये है, ये थोड़ी सी ज्यादा. We'll add this vector plus this vector. So the difference of these two distances from a given point, we can represent. अगर first term in Taylor's expansion लेंगे, we'll accordingly expand this term.
X naught क्या लेंगे इसका मान?
कौन सा x?
X dash क्या लेंगे?
x dash है ना ये distance.
ये तो पॉइंट होना चाहिए ना, नॉट एक्सटेंशन.
कौन सा x? I don't.
इधर एक्सपेंशन में x naught इज नॉट एक्सपेंशन स्क्वायर.
ये है ना, ये है ना बाहर ग्रेडियंट है ना, डेरिवेटिव.
डेरिवेटिव है
d by dx of d, first term d by df of.
doing the expansion we expand out the point.
हाँ ठीक.
X dash should be point not distance.
X dash should be point, not the distance.
Point is not we can.
ना it's the distance between two neighboring points के दरमियान डेरिवेटिव कैसे चेंज होता है. एक तो आप अपना लीजिए a, f of a पहली टर्म, दूसरा आप लेते हैं a into f dash x minus x प्राइम, ऐसे लेते हैं. फिर तीसरा लेते हैं a f का ट्रिपल डैश, फुल है जो ये डेरिवेटिव है ना बाहर. You can accordingly take it. First term, second term, third term. It's understood in this term. You can take a first term, फिर second term.
Here we can take x dash as distance.
हाँ, x dash is distance. And then corresponding neighboring points between these two distances, which correspond to these two surface layers of the charges, which measures the field at this point, dipole at this point. ठीक है. So you are trying to see things from this, यहाँ से यहाँ तक क्या है, फिर यहाँ से यहाँ तक क्या है, फिर difference of both of them. First order expansion, second order GB. तो यहाँ तक तो ठीक है ना? हाँ ठीक है. Now we can have जो इसका है, we'll write it in terms of dipole moment. P को हम ऐसे लिखेंगे, n times d into dA. So if you write it this way, so I'll just rub it off. तो phi को हम ऐसे लिखेंगे, So if you write इसको dipole distribution को in terms of dipole moment लिखेंगे, we'll write it like this. And further, what we are going to do, n dot of del prime 1 by x minus x prime. So we can also represent it in terms of solid angle. इस चीज को हम solid angle के साथ डिनोट करते हैं. Solid angle है ना, dA cos of theta. So can we write it as cos theta dA divided by x minus x prime. इस सब को हम in terms of solid angle लिखेंगे. We will write it further in terms of, क्योंकि ये है ना, ये डेरिवेटिव है इसकी सब. So you convince yourself, can we write this thing in terms of solid angle or not? ठीक है. Solid angle क्या है बेसिकली? Solid angle है जब आप करते हैं ना कोई भी सरफेस होता है, तो कितना फ्लक्स आप निकालते हैं इस छोटे से एरिया में, फिर उसी को इंटीग्रेट करते हैं पूरे इसमें. अब इसी में ये है कि यू कैन So यहाँ से यहाँ तक जो है change, can we write it in terms of solid angle or not? So you just think over it at your place. Okay, at this point. So if you write it, so we can write it. We can write phi x को हम लिख सकते हैं. तो इस सब के बदले हम लिखेंगे in terms of d rho. We are calculating field and उसका solid angle क्या है साथ में. Field 1/4 pi epsilon naught s या d x हो. So this is a surface dipole moment density. आप नॉर्मली इन योर अर्लियर क्लासेस पढ़ते हैं ना, गॉसियन पिल बॉक्स एक पढ़ते हैं ऐसे. नॉर्मली इलेक्ट्रिक फील्ड ड्यू टू शीट ऑफ चार्ज ऐसे करते हैं ऑन वन साइड, ऑन बोथ साइड शायद करते हैं सिग्मा बाय. अब दिस प्रॉब्लम इज सॉर्ट ऑफ सिमिलर टू दैट प्रॉब्लम. यू हैव अ सरफेस चार्ज डिस्ट्रीब्यूशन and there is another charge distribution. They are closely neighboring. अब such that जो उनका contribution at a given point है of one surface and other surface, it may not always add. It may oppose each other. It may be in the same direction or it may be in the opposite. So minus normally आता है. So that's what we are doing. So we will write the phi 2. If we write it in terms of the difference of potentials due to these two surface charge distributions, जिसकी वजह से dipole produce हो रहा है, ठीक है. तो we can write phi 2 minus phi 1 is d by epsilon naught. हाँ. तो लास्ट में हमने लिखा था, लास्ट वाला लिखा था इसके साथ phi 2 minus phi 1. हाँ. Due to one and due to another. You can write it like this. So what I recommend you go to this book. इसमें आप this जो paragraph है ना, this paragraph you read it twice thrice, ठीक है, and then we can really understand it अच्छी तरीके से. We stop today, ठीक है. एक काम करो आप थोड़ा सा ना सवेरे, इसकी फिर मिस हो जाता है ना, फिर समझ नहीं आता आपको. मैंने ये पढ़ा था ना इसकी कंटेक्स्ट में.